Good morning, everyone. Welcome to today's webinar, A10 plus Big Switch, Next Gen Cyber Defense for DMZ. My name is Bala Ramachandran. I'm the Director of Product Management responsible for technology partnerships here at Big Switch, and I'll be your host for today's webinar. So as we go through the presentation, please feel free to ask questions using the Q&A box on your webinar dashboard. If you're watching this video on demand and you have a question regarding today's topic, simply go to bigswitch.com/webinars and submit a question using the link provided. We also provided you with handouts for today's session. The A10 solution brief plus the information on Big Switch Labs is available via the webinar dashboard. You can download them from the handouts tab in the right-hand corner of your dashboard. So without much further ado, let me introduce you the panelists for today's webinar. I'd like to welcome Rich Groves, the Principal Architect at A10 Networks. Welcome, Rich.
Thank you, Bala.
And Ted Elhorani, Technical Marketing Engineer at Big Switch Networks.
Thanks, Bala.
So we have a full agenda for today's webinar. Let's get started. Our first speaker, Rich Groves, will talk about the BIGSECURE architecture, which I'll talk to you briefly about to set the context. And then we will then move to a presentation by Ted on another solution, inline solution with the A10 SSLi product. So just to provide some context for this webinar, so as we all know, DMZ is a gatekeeper of the data center. It's the place where a slew of security tools are deployed, and traffic potentially needs to go through multiple of these tools. For example, firewalls, SSL visibility, appliances, IPS, web proxy. In addition, different types of traffic need to go through different set of tools, which in other words means that we need to create multiple tool chains. Now, if you look at legacy solutions, they leverage technologies like policy-based routing rules to steer traffic through these tools. These are complex and hard to use, and it's very hard to create dynamic service chaining logic. So today, Big Switch has a solution called Big Monitoring Fabric Inline solution, which uses an SDN-based approach to tremendously simplify and manage these dynamic service chains. The solution leverages open networking hardware managed by central SDN controller software, and the controller acts as a central point to configure multiple policies to create different paths through the inline tools. For example, today we will be talking about the joint solution with A10 SSLi, where you could send SSL traffic through the A10 SSLi and IPS, which is attached to the chain, while you may want to send the non-SSL traffic to bypass the SSLi device. So Ted will go into the details of this solution as we move along in this webinar. But one of the things that we are observing today is that the complexity of attacks are increasing and becoming larger scale, as we noticed with the recent Mirai botnet attacks, which are so securing the data center from such attacks is becoming more and more complex. So A10 and Big Switch have collaborated on a new architecture known as BIGSECURE, which leverages SDN programmability and scale out for mitigation of attacks of such magnitude. So we'll have Rich from A10 go through this, but as Rich goes through this architecture, we will see how SDN enables software-defined security and intent-based security to combat next-gen cyber defense. Over to you, Rich.
Thank you, Bala. As Bala stated, my name is Rich Groves, and I'm with A10 Networks, and I'm here to talk to you about the BIGSECURE architecture using BigMon and the A10 Thunder threat protection system. Next slide. But first, I wanted to give you a little bit of background and why we even started talking about this. So as many of you likely know, toward the end of 2016, we had an issue with the Mirai botnet, we being the entire industry, and in fact, the entire internet. Mirai itself is a collection of infected IoT devices, like cameras, DVRs, printers, routers, etc. And it grew to approximately 600,000 unique sources, so unique devices, in late 2016. There have been cleanup efforts that have reduced the scale and scope, but really, you know, it's important to note that since we are talking about Mirai, but Mirai is just one of multiple IoT botnets that we will unfortunately have to see within the upcoming years. So why has it been effective? Its size. It has a very large footprint of real devices, as you can see above. Oddly enough, in the DDoS space, you know, to create lots and lots of traffic toward an end node to bring them down, normally we see amplification, and we'll have to, that's a complex topic that we'll have to go through in another webinar, unfortunately, but we'll see amplification to just increase the amount of traffic heading toward an end node. With an IoT-based botnet, however, there's not as much of a reason to employ amplification. So you'll see in Mirai, Mirai has very little to do with any reflection or amplification techniques. Mirai is easy to use. It includes some classic flood mechanisms in the toolkit, like GRE, UDP, and SYN floods. But it also has other multi-vector attacks that are more relevant to server resources. With Mirai, you have sort of the combination of server attacks and network infrastructure attacks. Some examples of those are the stomp attack, which is the ability to set up an actual real TCP session between the IoT device and the end node, and just sort of, you know, pump a lot of traffic down that pipe. DNS water torture was one of the primary attacks that brought down a large portion of the internet recently, and HTTP and, you know, L7 attacks essentially. The Mirai IoT devices look like real hosts on the wire, mostly. So we have real IP addresses. That means setting up a real TCP connection, which is different than these floods and amplification techniques. And it has the ability to bust through some of these authentication challenges that a DDoS device an anti-DDoS device might throw at an attacker. Sending a 302, like an HTTP redirect, for example, the IoT device here knows how to get around that challenge technique. And when it comes down to it, more sophisticated attacks, more sophisticated attackers, such as this, require more compute resources to detect and mitigate. For the DDoS vendor, the anti-DDoS vendor, this isn't so bad, because that means buying more capacity to keep up. But really, from the user's perspective, this is not cost-effective to just keep up by buying mitigation and detection devices. Next slide. So the current solutions are really lacking, especially in this SDN DevOps environment. Capacity is static. Now, this is pretty straightforward, but the idea here is that since this mitigation capacity, which is really costly, and essentially stranded during peacetime when you're not under attack, statically configured mitigation clusters are actually really costly building blocks to achieve scale. This sort of goes with the previous bullet point. And then this lack of dynamic scale-out function, as you'll see in the BIGSECURE architecture, means that mitigation capacity, when it's needed, you have to buy more stuff, essentially, and buy more hardware. The current systems lack a full-featured API. So you'll see in DevOps environments, like many of the ones that we deal with, most of these devices have to be driven programmatically. And if there isn't a full-featured, for example, RESTful API like the A10 Thunder TPS employs, it makes it very challenging. And each one of these devices gets to see a lot of traffic, right? So it compiles a lot of statistics, very interesting statistics, but with the current solutions that are in play, many of them are sort of locked up, you know, not retrievable through these APIs and other standards-based methods. They lack true SDN-enabled actions. And you'll get to see this in the demonstration here coming up, how BIGSECURE enables this. But what I mean by SDN-enabled actions is taking a primitive that can be boiled down to, let's say, layer 3, layer 4, etc., and programmed into a switch chip to be able to not just steer traffic, but to be able to block. These guys don't enable that for the customer. There's a real lack of focus on availability. We're talking about a DDoS attack here, but the fact of the matter is, if your service isn't available, it looks like a DDoS attack no matter what, right? And so current solutions really have no focus itself on keeping the service up, even in times of, let's say, flash crowds or other good effects. Next slide. So that's where we start looking at what the optimal solution, right, technically is to deal with this. And this is where we came up with BIGSECURE. So you can see that we have up at the top of the graph here, you know, of the graphic, we have an SDN-enabled fabric-based filtering and traffic steering. So these icons we have up at the top are BigMon switches. The idea here is we have a well-known attack signature that can be plugged into these switches, actually program the switch chip itself to drop those at the edge where they really should be dropped. And then we can surgically forward only the traffic requiring mitigation and some other behavioral analysis to devices that do higher layer analytics like the A10 Thunder TPS. In the next layer down, we see this area for multi-vector attack mitigation. This is really where we start talking about the scale-out capacity to be able to deal with higher layer functions that are really costly on the CPU and memory. So we scale up or scale down on either detection or mitigation function as needed. Performing these higher layer mitigations, as we talk about, is very costly. We can do that with this larger sort of scale out shared capacity. Enforcing granular policies, this is something that Thunder TPS does very well in this layer, per source, per dest, per source and dest, at very, very large scale, millions and millions. And finally, adding more availability and security services into these service chains that we're talking about here, such as A10's DNS firewall or web application firewall, even caching, DNS caching and HTTP caching. These are all functions that we employ in this sort of availability plus scrubbing center, you know, that we're looking at based on the BIGSECURE architecture. Next slide. So this sort of illustrates what we had talked about here. So Thunder TPS doing some attack detection, creating baselines of traffic. The TPS invoking the BigMon API, this SDN-enabled action that we talked about for alerting of this DDoS attack. And then the BigMon controller has the ability to not just program these custom rules into the switch chips that we talked about for amplification filtering, but here it's for this sort of surgical steering of traffic toward the scale-out cluster that you get to see here with the vThunder TPS VNFs that are able to be scaled out for all this intensive source-based mitigation. So Bala, I'm going to hand it off to you, and we can go ahead through the next section.
Thank you very much, Rich. It's been great to collaborate with you and your team on this very innovative architecture. So what I can see is clearly software-defined security leveraging SDN with advanced security becomes a necessary ingredient for managing these next-gen cyber attacks. So thank you for that. And now we will see this architecture in action with a demo from Ted. Over to you, Ted.
Thank you, Bala. So let's go first over the setup that we have for this demo. What you are seeing in front of you here really is a typical scenario where a DMZ is deployed right in the middle to defend a DNS server, in your system against Mirai Botnet style attacks. The green arrows that you see represent peacetime traffic flow. These valid DNS requests come through the edge router, reaching the first endpoint of BigMon on the inline switch. And from there, what we do is we configure the BigMon inline switch through the controller to make copies of this traffic, to mirror this traffic, and send it to an out-of-band Thunder TPS appliance. We have then also inserted an inline virtual TPS service on that same chain, security chain. And that service is really using two lag interfaces that we have defined earlier on that switch. VTPS lag 1 is used to send the traffic to the VNF, and VTPS lag 2 interface is used to receive traffic back from the VNF service. Now, initially in peacetime, we don't really need to have rules matching traffic to send to these DNFs. All we need at this point is really to send the traffic out of band, to mirror that traffic and send it to the out of band TPS for detection purposes. Now, the next step in the demo will be to send the attack-like traffic, and this traffic will be, consisting of malformed DNS requests that are coming at above baseline rate. And again, this traffic will go to the out-of-band TPS appliance, and the A10 TPS appliance will detect that attack because it sees this is not normal traffic, it's not coming at baseline rate, and it consists of malformed DNS requests. And once that detection happens, it will use the BigMon API to pass the attack parameters, what server is being attacked, what type of traffic. And with this information, the BigMon controller will reprogram the inline switch, this time to redirect to steer traffic to the inline DNS. So the traffic, the entire attack traffic and valid traffic will go to the DNF, where we will scrub it and send back only the valid DNS requests. The traffic will continue on that security chain, and our DNS server will only see the valid requests. Now, as the attack proceeds and we have traffic exceeding a preset threshold, we spin up additional VNFs with corresponding interfaces of that server where the new VNF is instantiated the interfaces of that server, we add them dynamically to the lags that we have, so that the traffic that is coming in gets redistributed across our DNF pool. And we'll go over these details in a little bit. So let's head on to the demo itself. So starting, we will be with, we're seeing the big chain interface. We see a security chain that is defined on Ethernet 1 and Ethernet 2. Ethernet 1 is really facing the edge router. This is where your traffic that is coming to your DNS surface is first showing up. It's coming from the, it could be from the botnet, or it could be validated traffic. And Ethernet 2, this is where you attach your data center core router, and behind which you have your DNS server. Now, over this chain, first, as we said earlier, we have the out-of-band TPS service. So let's go ahead and look at the configuration of that out-of-band service for mirroring the traffic. So this is the span service, and we look at specifically the rules that have been configured for the span service. So we'll edit the service and take a look at the rules. And as you can see, we have only selected UDP traffic. We're only interested in this case in UDP traffic. We want to mirror that traffic and send it over to our out-of-band A10 TPS appliance. Next, we want to take a look at the inline VTPS service. So let's edit that service and take a look how it's configured. As you can see, we have the interfaces for this service being the VTPS lag 1, link aggregation group 1, and VTPS link aggregation group 2. And we'll come back to these interfaces in a little bit. Before we do that, let's go ahead and take a look at the VTPS service configuration. So as you can see in the rule set here, we have no rules configured. There is no matching traffic because we are in peacetime right now. No traffic needs to go to the mitigator. All we care about is to send our traffic to the detector in an out-of-band mode. And back to the lag configuration. So we said we have two lag interfaces configured on the switch. The first lag interface, VTPS lag 1, that will be used to send the traffic to the inline VTPS service, has one member interface, Ethernet 43, and the second lag interface has one member interface, Ethernet 44. So this is the initial configuration that we'll start with. And as we see later, as the attack proceeds, we will see that additional members are added to these lag interfaces for scale-out purposes. So let's go ahead and take a look now at first the DNS server. I'm sorry, on the out-of-band box, or the A10 Thunder out-of-band box first. So the out-of-band box is now actually receiving the peacetime baseline rate of traffic. So you can see here that we have about 100 packets per second rate of traffic that is coming in. And the VTPS 1 inline has no traffic, as we just mentioned earlier, because we are in peacetime mode. Now, the DNS server is receiving that peacetime traffic, the expected 6 kilobytes per second amount of traffic. And the next step for us is really to generate that attack-like traffic from a attack server. So what we're doing here on the attack server, we're generating UDP traffic destined to our DNS server at 9.98, and it's UDP traffic headed to port 53. Note also that we are randomizing the source of this traffic, so it will look like Mirai style botnet attacks. So we go ahead and start the attack. And this is on the DNS server. We see here that there is a sudden increase in the rate of traffic, about 440 times the peacetime traffic that is coming in. And then all of a sudden, we go back to our peacetime rate of traffic of 6 kilobytes per second. So this tells us that the mitigation has occurred and it was successful. Now, looking at the VTPS inline appliance, we see first in the UDP section that there was a sudden spike in the amount of dropped packets, the red line, to about 60K packets per second. And then that rate has dropped to about half. So why did this happen? Why did we have the rate of drop packets go down to about half the original peak? As you remember earlier, we mentioned the scale-out behavior of BIGSECURE. So once we have detected the attack and we steer the traffic towards our inline VTPS, we have also been looking for the threshold that we need to exceed before we scale out our service. So this is what actually happened. When the attack exceeded this threshold, we autonomously instantiated a second VTPS and added the corresponding member interfaces to the lags and distributed that traffic across 2 instances. And that's why you see like the half of the traffic being received at this point.
Thanks, Ted. That was very interesting. So Ted, with this approach, the promise of intent-based security is now becoming real, and traffic redirection for mitigation is automatically done. Scale-out mitigation is possible in order to handle high bandwidth attacks. Security intent can be immediately implemented through automation, through API integration. So time is of essence with security issues, and a dynamic architecture with fast response is very critical. And with this, security really becomes real with this architecture. So that's great. There are a few questions which we are getting. We will address those in the Q&A section. But there is one question which I wanted to ask Rich at this point. So usually the internet pipe is the bottleneck in mitigation. How do you deal with 200 GB attack if clean pipe is only 100 GB?
It's a really good question. So we have a couple of methods here, and they sort of merge into this BIGSECURE architecture. With access to full-featured APIs, SDN APIs, like we're talking about, we have a partnership. Also, we at A10 have a partnership with VeriSign using their open API. It's a RESTful API to essentially trigger a redirection toward a network with a much larger capacity for mitigating. You know, clearly it's hard to keep up with buying mitigation capacity, as you're alluding to, but you know, that also is the case for buying links and buying bandwidth, and so that's definitely part of it. So it is truly a multi-layer approach.
Thank you, Rich. So next, we'll switch gears, and Ted, if you could talk about the BigMon inline solution with the A10 Thunder SSLi for SSL visibility, that would be great. So, thank you, Ted.
Thank you, Bala. So in the second part of the webinar, we will cover the topic of SSL visibility with BigMon A9 and the A10 SSLi appliance. Today, it's widely recognized, there is consensus in the industry that web traffic will increasingly be encrypted. Earlier this year, there were widely reported information that traffic on the Mozilla Firefox browser is more than 50% encrypted traffic. And the trend is clearly in favor of increasing rates of encryption. A few years back, the SANS Institute warned the community that a large number of attacks, malware, malicious attacks will be actually hidden in this encrypted traffic. So although increasing encryption is a great thing for the entire industry, we also have to be careful about hidden attacks in this encrypted traffic. Recently, the Ponemon Institute had a survey in which about 41% of IT practitioners confirmed that attacks are carried within encrypted traffic. Now, where is the problem here? The problem is that in today's legacy systems in the DMZ, we have very rigid designs. Our tools, like our IPSs, our inline mitigation tools, typically are blind to SSL traffic, to encrypted traffic. And there are a few things we can do. We can go ahead and add SSL visibility to each one of these tools, but this is problematic from many perspectives. First, there's the additional cost. Second, there is the inefficiency of decrypting and re-encrypting at every step of the way in the DMZ. Now, an alternative is to reinsert SSL visibility within the chain, within the security chain. But again, here we run into the same problems of inefficiencies. As we add more tools that need to look at decrypted traffic, we have to make sure that these tools are within the decrypted zones in our DMZ chain, and this adds a lot of extra, operational challenges to the administrator. Now, enter the solution that we have with A10 SSLi, BigMon plus A10 SSLi. What we do is we create a decrypt zone in our architecture. Starting with the typical design, we have traffic coming through from external traffic coming through and going to our, let's say, FireEye appliance. However, this encrypted traffic, because it's encrypted, the FireEye appliance cannot do much with it. Now, what we do, we insert inline the A10 SSLi appliance, and that creates for us this decrypted zone right in the middle. And within that zone, we can insert inline services like the FireEye appliance. With this architecture in place, the FireEye appliance or other tools can look at decrypted payloads and perform the mitigation and threat protection that needs to be done. So now let's take a quick look at the traffic flow in this architecture. So first, our client will be sending traffic through our firewall to the big monitoring fabric inline switch. The encrypted traffic will reach endpoint 1. We have also inserted the SSLi, A10 SSLi inline service, and we send that traffic inline to the first partition of the service where we decrypt the traffic, send it back to the inline switch, and now we are free to insert any number of inline tools that will be able to look at the decrypted traffic. Once we are done with looking at the traffic, we send the traffic back to the inline switch. From there, it goes again to the A10 appliance. It gets re-encrypted and sent back to the switch, and from there to its destination. Now, let's take a look at the steps of the demo that we will go through. So the demo is really two parts. In the first part, we have the FireEye NX series appliance inserted in the encrypted zone. Noted that the box is in the encrypted zone. That means when the traffic comes in, it will only see encrypted traffic. It won't be able to detect and alert against malware. And the traffic, of course, will continue and will hit the service. In the second part of the demo, we will show you how easy it is to move a service like the FireEye service to the decrypted zone that we formed with the A10 SSLi appliance. And again, we repeat the same test. This time, however, the traffic will go from the client, the encrypted traffic. It will hit the A10 box, gets decrypted, and then we send it through our FireEye appliance. And we'll see how we can, looking at the decrypted traffic, how we can detect the malware and perform our threat protection. So let's head over to the demo. So what you're looking at here first is the configuration on the A10 SSLi appliance. We have two partitions. We have a decryption partition configured over two physical interfaces, Ethernet 1 and Ethernet 2 of the appliance. And we have a second partition, the re-encryption partition, configured over physical interfaces Ethernet 3 and Ethernet 4. We also have the FireEye appliance, and as you can see, there are no alerts currently. This appliance is inserted inline first in the encrypted zone. So it won't be able to see the decrypted traffic, and it won't be able to perform its function properly. So what you're looking at now is the BigMon interface. We go ahead and look at the security chain that we're going to configure. So the security chain has two endpoints. Endpoint 1 is attached to Ethernet 1, and endpoint 2 is attached to Ethernet 2. And Ethernet 1 is really facing our DC router and our clients, and Ethernet 2 is facing the edge router and the internet. So we'll go ahead first and insert the inline services, specifically the A10 SSLi appliance. And note we have two services. There is an SSLi inside for decryption, and we'll also insert the SSLi outside for re-encryption. And these, by the way, can be the same physical appliance. We'll also insert the FireEye NX appliance. And we'll intentionally keep it outside the decrypt zone. So note that it's not between the two SSLi A10 services. So we'll go ahead from here and perform a test. So what we're doing here is we're making a request to a file that is hosted on a S3 bucket. This file, we're trying to load this file, and this file contains malware. So the file has loaded, and we can go ahead and take a look at the contents of the file that we loaded. And as we scroll down, we see that the entire file has been loaded and no mitigation was performed, as expected in this case. So the entire code was loaded in. Now the next step, which is the essential step here, is really to move our FireEye appliance and put it inside the decrypt zone. And this is as easy as drag and drop with the BigMon interface.
Okay, awesome.
Okay, now that we inserted the appliance in the decrypt zone, we'll go back and perform the test again. So we try to load the same page. And if we head over to the FireEye appliance and reload the interface, we'll see that there is detection of malware. And we have the right parameters for our client and the destination server. Now we can go back and double check to see what got loaded in our browser. So we look again at the source and scroll down. And this time we see that only part of the code has been loaded, so the code is truncated and mitigation took place. So what happened is that the FireEye appliance successfully blocked the traffic, given that it can look at decrypted traffic. And that concludes our demo. Now back to you, Bala.
Thank you. Thank you very much, Ted. Thanks. That was very, very informative and very useful to understand how the dynamic nature of our BigMon inline solution with A10 SSLi works. And so let's now switch gears, and there are a few questions which we have from our attendees. So let me ask you some of these questions. First one, is are there capabilities on the Thunder TPS to address DNS challenges? Rich, do you want to take that?
Yeah, of course. Yes, definitely. We do a number of them, all the way from a pretty nifty drop and retry interval at the UDP layer. But we also do the sort of standard truncate bit move traffic to TCP, expect traffic from that source, and we have a few others. So yes, definitely.
Great. So the next question is, do you threshold traffic based on L4 values, or is it baselining L7 also, like queries per second, mix of DNS traffic, and so on? And
Sure.
I think a follow-on is, what is the baselining interval for legitimate traffic?
Got it. I'll answer the interval first. So the interval is configurable. We have recommendations depending on the service. Oftentimes it is a week, of baselining, but certainly some can be done for a day and still be very valid. In the other question, we currently do thresholding, compile these threshold values based on L4 information, but we support the mitigation based on numeric values for L7 information as well. It's the automatic baselining that's done with some of these L4 values. What we do find is that in and of itself it takes care of a lot of problems, especially you look at what Ted was talking about with encrypted traffic. It becomes very challenging to baseline at L7 if we can't actually see the traffic, right? But for DNS traffic, we definitely have policies for, as you're saying, A records, quad A's, etc. Currently, we're doing the baselining at L4.
Great. Thank you, Rich.
Yep.
Those are all great insights, and thank you, Rich and Ted, for great presentations. If something we discussed here piqued your interest, or you'd like to know more, just head on over to our website, bigswitch.com, or you can send us an email at info@bigswitch.com. Now, we make it easy for you to get started with BigSwitch solutions. There are several resources you can download or watch that will provide you a tour of our products. So with BSN Labs, you can experience BigSwitch Networks, open networking SDN solutions firsthand from the comfort of your PC. We believe that there's no better way to learn about a product or technology than to take it for a test drive. So for free, hands-on experience with our SDN Fabric products, you could visit labs.bigswitch.com to get access. So all of our past webinars, including this one, will be posted online at bigswitch.com/webinars. Our next webinar is on Wednesday, April 12th at 10 a.m. Pacific. The topic is the first of a 4-part series featuring Big Cloud Fabric graphical user interface as a single pane of glass into the network. And then we'll also have a special edition SDX Central webinar on April 18th. So look out for emails for registering for these webinars. Well, that concludes our presentation for today. Thank you all for joining us, and we'll see you next time.